For as long as we've looked up at the sky, we've asked that one big question. How did this all begin? But there's another mystery, maybe even a more profound one, that we're going to tackle today. And it's the question the cosmologists are wrestling with right now.
Yeah, how will it all end? Is it going to expand forever and just fizzle out into nothing? Or is everything going to come crashing back in on itself? For decades, that was one of the biggest questions in all of science. And the answer we're starting to get? It is not what anyone expected.
All right, Section 1, a cosmic question. So to really get a grip on our ultimate fate, we've got to rewind the clock a bit, back to a discovery that completely turned everything we thought we knew about the cosmos on its head.
Okay, so for most of the 20th century, the thinking was pretty straightforward. The universe is full of, well, stuff. Galaxies, stars, all of it. And all that stuff has gravity. So that gravity should be acting like a giant cosmic brake, right? It should be slowing down the expansion that started with the Big Bang. Makes sense. But then, 1998 happened. Astronomers looking at distant supernovae found something that blew their minds. The expansion wasn't slowing down at all. It was actually speeding up. Something out there is hitting the accelerator.
Next up, the runaway universe. This discovery was a game changer. It meant there had to be some kind of mysterious anti-gravity force out there, a force that was somehow winning the cosmic tug-of-war against gravity itself.
And scientists gave this mystery a name: Dark Energy. Now, let's be clear. We have no idea what this stuff actually is, but we know what it does. It acts like this cosmic repellent, pushing everything away from everything else. And understanding the true nature of this energy, well, that's the single biggest clue to figuring out how this whole story ends.
And here's the part that's just staggering. It's how much of this stuff there is. You take all the stars, all the planets, every galaxy, all the normal matter we can see, and even the dark matter we can't see, and all of that together, that's only about 27% of the universe. The rest of it, nearly 3/4 of everything that exists, is this completely unknown dark energy. So, how in the world do you get a handle on something like that? Well, to predict how it behaves, cosmologists focus on one key property, and they boil it down to a single number. They call it the equation of state, or just W. You can kind of think of W as its power rating, like how strong is its anti-gravity push. And as we're about to see, the exact value of that one little number, it determines everything.
Okay, so Section 3, 3 possible fates. Because depending on what W is, 3 totally epic and wildly different scenarios for the end of the universe pop out.
All right, first up, we have the big freeze. This happens if W is exactly -1. If that's the case, dark energy is what's called a cosmological constant. Basically, its strength never changes. It just keeps pushing and pushing forever. The universe expands and expands. Eventually, distant galaxies will be so far away they'll disappear from our view. Stars will burn out, and the entire cosmos will just slowly fade into a cold, dark, and incredibly lonely emptiness.
But what if W is less than -1? Well, that leads to a possibility that is frankly terrifying: the Big Rip. In this scenario, dark energy is something called phantom energy. And what that means is its density actually gets stronger as the universe expands. Its repulsive force just grows and grows and grows until absolutely nothing can stand against it.
And the timeline for this, it's horrifyingly specific. Let's say W is -1.5. The destruction unfolds in stages. About 1 billion years before the end, entire galaxy clusters get pulled apart. Then 60 million years before the end, our own Milky Way gets shredded. 3 months out, the solar system is torn apart. The final 30 minutes, the Earth explodes. And in the very last, tiniest fraction of a second, the fabric of reality itself unravels as atoms are ripped apart. It's the ultimate cosmic demolition.
Okay, so our third option is the Big Crunch. This is what could happen if W is greater than -1, or if there's a different kind of cosmic force at play that's actually negative. In this case, dark energy's push gets weaker over time. Eventually, gravity would get the upper hand, win that cosmic tug-of-war, stop the expansion, and then pull everything, all of it, back together into one final, super hot, super dense, fiery collapse.
So there you have it. Those are the big 3 possibilities. And it all comes down to that one little number, W. A long, cold freeze, a violent rip, or a fiery crunch.
Now, for years, the evidence we had seemed to point to the big freeze. The data showed W was really close to -1, but then a new clue showed up.
Section 4. A new clue. This brings us right up to today. Thanks to some massive astronomical surveys, we now have these incredibly precise measurements that have given us our sharpest ever look at dark energy. And what they found, well, it's a clue that has changed the entire game.
And here it is. This is the smoking gun. Data from the Dark Energy Survey and another project called DESI, it suggests with really high confidence that W is not equal to -1. What that means is dark energy isn't some constant, unchanging force. It's dynamic. It's changing over time. And that pretty much rules out the simple big freeze scenario.
So if it's changing, what's causing it? Right now, the leading theory is something called the Axion Dark Energy model, or ADE. And it suggests that what we call dark energy isn't just one thing. It's actually a combo of two different forces. You've got this constant background energy, we call that lambda, and then you have a second energy field that actually changes over time. And it's the way these two interact that seems to perfectly explain the new data we're seeing.
All right, final section, our universe's lifespan. Because when scientists took this new AD model and plugged in the latest data, they uncovered something absolutely startling, an implication for our future and for the total lifespan of our universe.
And here's the bombshell. The version of the model that best fits all our observations is one where that background energy, lambda, isn't pushing things apart. It isn't even neutral. It's negative. And a negative cosmological constant doesn't push, it pulls. It's like a subtle background gravitational force that's always been there. And what it guarantees in the long run is that the universe will stop expanding and it will collapse.
This model actually predicts a very specific path for our universe. You can see it in this chart. The solid line shows the size of the universe over time. It's going to keep expanding for a while, but then it's going to hit a peak, a maximum size, in about 11 billion years from now. And after that, it reverses course and comes plummeting back down towards zero. In other words, a big crunch.
And the model doesn't just predict what will happen, it predicts when. It gives us a number. This isn't an infinite future. It's not some random doomsday. It's a calculated total lifespan for our universe, about 33.3 billion years.
So let's put that into perspective for a second. Our universe, right now, is about 13.8 billion years old. That means we're only about 40% of the way through the entire show. The final curtain call, that big crunch, is slated to happen in roughly 20 billion years from today.
Now, of course, this is all based on a model, and it's got to be tested more. But it's an incredibly powerful and specific prediction based on the best data we have right now. It completely changes how we think about the cosmos, transforming it from this maybe infinite, endless stage into a finite story, one with a clear beginning, a middle, and a definitive end. So I guess the final question is, if the universe has an expiration date, what does that change for us?